In 2004, something happened that most people never heard about. On December 27th, a burst of energy hit Earth. Not a meteor, not a solar flare, something from across the galaxy. It came from a dead star, a spinning, collapsed core of matter so extreme that scientists still argue about how it exists at all. The burst lasted less than a second. In that fraction of a second, it released more energy than our sun puts out in 250,000 years. Every satellite that was facing the right direction got hit. Instruments overloaded, data logs spiked and flatlined. Researchers staring at their screens couldn't even process what they were seeing. And here's the part that should bother you. That star was 42,000 light-years away, and it still nearly broke our instruments from the other side of the galaxy. Now imagine something like that, but closer. That's what we're talking about today. Not science fiction, not a thought experiment. Real objects, real physics, real stars scattered across our galaxy. Some of them spinning faster than any machine ever built by human hands. Some of them carrying magnetic fields so intense they can tear atoms apart from thousands of miles away. And at least one of them sitting right here in the Milky Way, on the very edge of collapse, growing heavier every single day. I want you to stay with me through this whole thing, because the story builds. What starts as a dead star gets stranger. It gets heavier. It gets more magnetic. It gets closer. And by the time we get to the end, you're going to understand why scientists don't just study these objects out of curiosity. They watch them like a clock they're not sure is ticking. Let's start at the beginning, or more accurately, at the end. When a massive star dies, it doesn't go quietly. The whole thing is a battle between two forces: the outward pressure of nuclear fusion pushing everything apart, and gravity pulling everything inward. For most of a star's life, those two forces are balanced. The star burns its fuel, holds its shape, and shines. But eventually, the fuel runs out. And when fusion stops, there's nothing left holding back gravity. The core collapses in a fraction of a second. And the outer layers don't collapse with it, they explode. That explosion is called a supernova. It's one of the most violent events in the known universe. But here's the thing people skip over when they talk about supernovas. Everyone focuses on the explosion, the flash, the shockwave, the cloud of gas that spreads across space for thousands of years. What they don't talk about is what's left behind, because once all that chaos clears, what remains sitting at the center is something that shouldn't exist. It's called a neutron star, and just the basic description of it sounds like someone made it up. A typical neutron star is about 20 kilometers across. You could drive from one side to the other in less than 15 minutes on a highway, if the surface weren't actively trying to kill you in about a dozen different ways. But inside that 20-kilometer sphere, there is more mass than our entire sun. Think about what that means. The sun contains 99.86% of all the mass in our solar system. Every planet, every moon, every asteroid, every comet, all of it combined is less than 0.5% of the sun's mass, and a neutron star fits more than that into a space smaller than most major cities. The density is so extreme that matter itself changes. Electrons and protons, the particles that make up atoms, are crushed together under the pressure until they merge into neutrons. That's where the name comes from. A neutron star isn't made of atoms. It's made of a sea of neutrons packed so tightly that a single teaspoon of the material would weigh over 1 billion tons. Not 1 billion pounds, 1 billion tons. If you somehow scooped a sugar cube-sized piece of a neutron star and dropped it onto the Earth's surface, it wouldn't land. It would punch straight through the crust, keep moving through the mantle, and not noticeably slow down until it reached the core. The Earth wouldn't stop it. The Earth would just be in the way. Now keep that in your mind, because we're about to make it worse. Some neutron stars spin, not the way Earth spins, one rotation every 24 hours. These things spin hundreds of times per second. When a massive star's core collapses, it conserves its angular momentum, which is the same reason a figure skater spins faster when they pull their arms in. The core shrinks from something the size of Earth down to a city-sized ball in less than a second. The spin doesn't disappear. It compresses, it concentrates, and what you end up with is an object the density of an atomic nucleus, rotating hundreds of times per second and carrying a magnetic field trillions of times stronger than Earth's. And as it spins, those magnetic poles, which aren't aligned with the rotational axis, sweep beams of radiation across space, Radio waves, X-rays, gamma rays, sweeping outward like the beam from a lighthouse. When those beams happen to sweep past Earth, we detect them as pulses, regular, rhythmic, machine-like pulses arriving from deep space. That's a pulsar. In 1967, a graduate student named Jocelyn Bell was analyzing radio telescope data and noticed something that shouldn't have been there. A signal, perfectly rhythmic, arriving every 1.3 seconds, precise to a millionth of a second. She and her advisor Anthony Hewish at first couldn't explain it. The signal was too regular to be natural interference, too consistent to be a glitch. For a brief period, they seriously considered the possibility that it was an artificial transmission from an intelligent civilization. They even labeled the signal source LGM-1, Little Green Men 1. It wasn't aliens, it was something stranger. It was a dead star, spinning and beaming, precise enough to rival an atomic clock, consistent enough to use as a navigation beacon, and powerful enough to beam radiation across thousands of light-years of space and still reach our instruments clearly. Once astronomers knew what to look for, they started finding them everywhere. Thousands of pulsars scattered across the galaxy, most of them ordinary, spinning fast, dense, sweeping their beams through space. But every so often, astronomers find one that redefines what ordinary even means. The one I want to talk about is called PSR J0952 G0607. That name isn't dramatic. It doesn't have a nickname most people have heard. But when you look at its actual measurements, you start to understand why scientists keep coming back to it. It spins at 707 revolutions per second, not 70, not 170. 707 full rotations every single second. Helicopter blades spin at around 400–500 RPM. That's revolutions per minute. This star completes 707 full rotations in 1 second. The fastest blenders on the market top out around 300 rotations per second. Industrial jet turbines hit maybe 500. This star leaves all of them behind, and it's been doing it for longer than our species has existed. The surface of this star, at that rotational speed, is moving at a significant fraction of the speed of light, and it's not flying apart, because the gravity is so intense, so crushing, that it holds the whole thing together despite the centrifugal force that should be tearing it to pieces. But the spin isn't even the scary part. Here's what makes J0952-0607 different from most pulsars. It's also the heaviest neutron star ever measured, nearly 2.35 times the mass of the Sun, all crammed into that 20-kilometer sphere. And that combination, extreme rotation and near maximum mass, is what puts this object in a category of its own. Here's why. Neutron stars have a theoretical weight limit. It's called the Tolman-Oppenheimer-Volkoff limit. The exact number is still debated, but most physicists estimate it somewhere between 2.2 and 2.9 solar masses. Beyond that point, the pressure generated by neutrons pushing against each other, called neutron degeneracy pressure, can no longer resist gravity. The structure collapses, and what it collapses into is something we'll get to in a moment, something you already know is coming, and I want you to understand exactly what the transition looks like when it happens. But first, how did J0952-0607 get this heavy? It didn't start this way. Neutron stars aren't born massive. They're born from the collapse of a star, and what's left behind is usually around 1.2 to 1.5 solar masses at most. So where did J0952-0607 get the extra mass? The answer is its companion. Orbiting this pulsar, at close range, is the dim, fading remnant of a star that used to be its equal. A white dwarf, the burned-out core of a dead star, being slowly torn apart. Gravity doesn't ask permission. The pulsar's gravitational field reaches out and pulls at the companion's outer layers. The material peels away, spiraling inward toward the pulsar. As it falls, it accelerates. It forms a glowing ring of superheated gas, an accretion disk, that feeds material onto the surface of the neutron star. Every gram of matter that falls in adds to the pulsar's mass. And it does something else too. It adds angular momentum. It spins the pulsar up, faster and faster over millions of years, the way pushing a spinning top keeps it from slowing down. Scientists call these systems black widow pulsars. The name comes from the spider, the female black widow that kills and consumes her mate after mating. In the astronomical version, the pulsar doesn't just destroy its companion, it eats it, slowly, methodically, atom by atom over millions of years, until nothing remains. And here's what that means for J09520607. Every day that passes, it gets a little bit heavier. Every gram of material it pulls from its companion pushes it a little closer to that upper mass limit. It's not a sudden crisis. It's a slow march toward a line that, once crossed, cannot be uncrossed. And the whole time it keeps spinning, keeps beaming, keeps pulling. At some point, we don't know when, the line gets crossed. And when it does, something happens that is almost impossible to visualize, because it happens in a way that produces almost no visible signal at all. The pulsar collapses. Not the way a building collapses, not the way a star explodes in a supernova. Silently, completely, in an instant that is both the end of one type of object and the beginning of another. The neutron pressure that was holding everything apart gives way. Gravity wins, completely and finally. And the entire mass of the star, already compressed into a sphere the size of a city, collapses further still, past any boundary we have a name for, past the point where matter, as we understand it, has any meaning at all. What forms in its place is a black hole. The radio beams go silent. The pulses we've been detecting from Earth simply stop. No warning, no flash, no final transmission. Just silence. One moment it's there, the next, nothing. From the outside, the object becomes invisible, but it doesn't become inert. Its mass is still there. The gravitational pull doesn't disappear. Space curves around it. Time slows near it, and anything that gets too close falls in and never comes back. There is one brief window, a matter of minutes or hours, where the surrounding environment gets extremely active. All that material in the accretion disk, still spiraling inward, is now feeding a newborn black hole instead of a pulsar. The magnetic structure that was keeping the pulsar's beams aligned is gone, but the rotational energy and magnetic fields of the newly formed black hole can, under the right conditions, produce what's called a relativistic jet, a focused beam of particles and energy shot from the poles at near light speed. If one of those jets happens to point anywhere near Earth, even from 14,000 light-years away, that's the distance to J09520607, the energy would be significant. This isn't speculation. Astronomers have proposed that a gamma-ray burst from an event like this may have contributed to the late Ordovician extinction roughly 440 million years ago, one of the largest mass extinction events in Earth's history. It wouldn't have hit us like a bomb. It would have silently stripped away the ozone layer, exposing everything on the surface to ultraviolet radiation from the sun. Marine ecosystems collapsed first, then everything else followed. The odds of J09520607's future collapse producing a jet aligned with Earth are low. Space is large and angles are rarely cooperative. But the fact that it's possible, the fact that it has happened before in Earth's history, is why scientists don't just note these objects and move on. They watch them continuously, because the universe doesn't send formal warnings. Now, I told you at the start that this story builds, and we've been talking about pulsars, fast, heavy, dangerous objects that are terrifying in their own right. But I want to introduce you to something that makes pulsars look almost gentle, something that doesn't need to spin at 700 times per second to cause devastation, something that doesn't even need to collapse. It just needs to exist. It's called a magnetar. And if a pulsar is a dead star that became dangerous, a magnetar is a dead star that became something else entirely. Here's the difference. A pulsar's magnetic field is already extreme, trillions of times stronger than Earth's field. That alone is enough to disrupt electronics, distort light, and affect the structure of atoms nearby. But a magnetar doesn't have a magnetic field trillions of times stronger than Earth's. It has a field 1,000 trillion times stronger. The number stops being meaningful to human intuition at that scale. So let's try to make it concrete. If a magnetar were located where the moon is right now, about 384,000 kilometers away, the magnetic field at Earth's surface would be strong enough to erase every hard drive on the planet simultaneously. Stronger than that, and the field starts pulling electrons out of their atomic orbitals. Stronger still, and the very chemistry that holds together the molecules in your body begins to break down. Not because of heat, not because of radiation, just because of the raw mechanical force of the magnetic field itself, pulling at particles that make up the things you are made of. The closest known magnetar is about 8,000 light-years away. Scientists have calculated that if one were within approximately 40 light-years of Earth, a single major flare could strip away enough of our ozone layer to cause a global extinction-level UV exposure event. 40 light-years, in galactic terms, is essentially next door. Our nearest stellar neighbor, Proxima Centauri, is only 4 light-years away. Now let me bring up December 27, 2004 again, because I want you to understand what actually happened that day with fresh context. The Magnetar was called SGR 180620. It was located in the constellation Sagittarius, about 42,000 light-years away. On that day, it experienced what's called a starquake, a catastrophic shift in its crust. Because magnetars don't just have powerful magnetic fields, they have crusts, solid surfaces made of incredibly dense neutron matter, held together under magnetic tension, that builds the same way tectonic stress builds on Earth, just billions of times more intense. When that tension exceeds the structural strength of the crust, the surface cracks, the crust shifts, the magnetic field suddenly restructures, and the energy released in that shift, in that momentary reconfiguration, radiates outward as gamma rays and X-rays at the speed of light. In less than a second, SGR 18620 released more energy than our sun will radiate over the next 250,000 years. Sensors on satellites in Earth orbit were immediately overwhelmed. The ionosphere, the electrically charged upper layer of our atmosphere, was measurably disturbed even on the night side of Earth facing away from the magnetar. Radio communications in some bands were disrupted. All of this from a dead star, 42,000 light-years away, that simply shifted its crust by a fraction of a kilometer. If SGR 180620 had been 10 light-years away, roughly twice the distance to our nearest stellar neighbor, Earth would have been in serious trouble. Not a gradual problem to be addressed over decades, a sudden global atmospheric event. That's a magnetar on a quiet day. Or rather, on one of its less quiet days. The strangest thing about magnetars might be how temporary they are. Their intense magnetic fields don't sustain themselves indefinitely, they decay. Over roughly 10,000 to 100,000 years, the magnetic field weakens. The starquakes become less frequent. Eventually, the magnetar quiets down into something closer to an ordinary neutron star. In cosmic terms, 100,000 years is almost nothing. Stars live for billions of years. Our galaxy is over 13 billion years old. A magnetar is a phase, a violent, brief phase in the life of a neutron star, and then it's gone. That means for every magnetar we can see right now, there were countless others that burned through their magnetic fury before humanity even existed, and went quiet without us ever knowing they were there. And here's the question that follows from that. What else has been happening out there that we don't know about? Because we're only seeing the universe as it was, not as it is. Every object we observe in the night sky is a message from the past. Light travels fast, 299,792 kilometers per second. But the universe is large enough that even at that speed, the journey takes time, a lot of time. When you look at J09520607, you're not seeing it as it is today. You're seeing it as it was roughly 14,000 years ago. That's before the agricultural revolution, before written language, before most of human history as we know it. If J09520607 collapsed tomorrow, crossed its mass limit and became a black hole, the news wouldn't reach us for 14,000 years. And if it already collapsed 14,000 years ago, we'd be about to find out. I want you to sit with that for a second. The pulses we're measuring today, the data scientists are analyzing right now, could be coming from an object that no longer exists. We are watching a star that might already be dead. Let's shift the scale again, because there's one more aspect of these objects that I think deserves attention, and it's strange in a different way from everything else we've covered. These stars, these ultraviolet, radiation-blasting, atom-destroying remnants of stellar death, some of them have planets, not many. Only about 0.5% of known pulsars have been found to host confirmed planets. But that 0.5% is enough to raise a question that's genuinely difficult to answer. How does a planet form or survive around the most violent object in its stellar neighborhood? The first confirmed exoplanet discovery in history, the first planet ever confirmed to exist outside our solar system, wasn't orbiting a sun-like star. It was orbiting a pulsar, PSR B1 2057+12, discovered in 1992, was found to have at least 3 rocky planets, all of them larger than Earth, all of them orbiting in paths that are elliptical, meaning they swing close and then far as they loop around the pulsar, spending part of their year bathed in radiation and part of it slightly further out. The pulsar itself was formed in a supernova explosion, so whatever planetary system existed before was obliterated, These worlds formed from debris, from the scattered remnants of whatever material didn't escape the explosion, gradually drawn back together by gravity over millions of years, cooling and clumping into rocky bodies. What would it be like to stand on one of those planets? There would be no sunlight, no warm, steady yellow star illuminating the sky. The sky would be permanently black. Every time the pulsar's beam swept past your position, there would be a pulse of radiation, a harsh, penetrating flash of X-rays rather than warmth. The surface would be exposed. Any life that existed would need to be deep underground, shielded by kilometers of rock, in subsurface oceans or caves where the radiation couldn't reach. And even then, the gravitational environment would be violent by any standard we're accustomed to. Tidal forces from the pulsar would stretch and compress anything caught in a close orbit. The ground itself would flex. And yet, something about those planets is resilient. They formed in the aftermath of a supernova. They survived the pulsar's radiation for billions of years. They're still there. Whatever those worlds are, they're made of tough material. Which brings me back to us. We orbit a calm, middle-aged star. Our sun puts out steady, consistent light. Our magnetic field deflects most harmful radiation. Our ozone layer absorbs the rest. We have liquid water, a breathable atmosphere, and a geologically stable surface. By any objective measure, we are in the quietest, most protected corner of our solar system's history. And that is unusual. That's not the default setting of the universe. The default setting is extreme. The default setting is crushing gravity and magnetic fields and radiation bursts and matter compressing until the rules that govern ordinary chemistry no longer apply. The existence of a calm place, our place, is the statistical outlier, not the normal case. So let me answer the question that started all of this. Should we be worried? Honestly, no. Not today. Not in any way that should change how you live. J09520607 is 14,000 light-years away. Even its radiation beams, sweeping through space every 1.4 milliseconds, would take 14,000 years to reach us. The Magnetar SGR 180620 is 42,000 light-years away. And its flares, as powerful as they are, dissipate with distance. The nearest Magnetar is 8,000 light-years away, still far enough that even its worst-case events pose no direct threat to Earth's surface. The danger is real. The physics is real. The events, collapses, starquakes, relativistic jets, these things actually happen. They have happened before in our galaxy's history. They will happen again. Some of them may have already influenced life on Earth hundreds of millions of years ago. But right now, we are safe. What these objects should change isn't your daily sense of safety. What they should change is your sense of scale. Because the universe is not a backdrop. It is not a quiet, empty stage that exists as decoration behind Earth's story. It is active. It is violent in ways that operate on timescales and distances that make human intuition useless. There are stars in our galaxy right now that are eating their companions, stars that are cracking open, stars that are spinning themselves toward the edge of what matter can physically withstand, stars that have already collapsed, silently, and we won't know for thousands of years. The galaxy isn't dangerous in the way that a car crash is dangerous, or the way a storm is dangerous. It's dangerous the way the ocean is dangerous, enormous and indifferent and operating on rules that don't make exceptions. We are afloat in it, comfortable, fortunate, separated from the worst of it by distance and time and the particular geometry of our location. But somewhere out there right now, a pulsar is gaining mass. Its spin is ticking upward. Its internal pressure is climbing toward a limit that, once reached, ends everything it is. And when it crosses that line, the pulses will stop. The signals we've been receiving for decades will simply disappear from the data. And in that silence, something new will begin. A black hole, born from the ruins of a star that survived a supernova, fed on its companion for millions of years, spun itself to the edge of physical possibility, and finally, quietly, gave way. No explosion, no warning, just a switch, flipped in the dark, 14,000 light-years away. And we'll be watching when it happens. Or maybe, we'll be watching for a signal that already isn't there. Looking into the sky, measuring the space where something used to be, wondering exactly when it ended, and whether something else is already on its way. That's the thing about the universe. It doesn't wait for you to be ready. It just keeps going, spinning, collapsing, rebuilding, sending signals across thousands of light years to a small, quiet planet that's only just beginning to learn how to read them. Keep looking up. Just maybe don't get too close.